Everyone, thank you, Dr. Baday, for the introduction. I appreciate that. So welcome to a new session. This time we are going to do some exercise together on stat questions. So this is the first time I am going to have this kind of a session. So I hope that we're going to have more. But this is the first time, just keep in mind, all right? So I'm going to share my screen. You don't need anything except an empty Jupyter notebook. So the way I'm going to go over is, today I plan to go over 4 questions, if time permits. I don't know how long it's going to take because it is the first time, okay? So please use one empty Jupyter notebook. If you don't have Anaconda installed or Jupyter Notebook installed, you can use Google Colab. Both are fine. So I will solve the probability question first and then try to write the code for it too. So that's the way I'll do my best to address the problem. So the questions I picked, there are 4 questions. So you can pick those questions, search for them from Glassdoor. So these are real interview questions asked, okay? And if you have any questions, please post your questions at Q&A so that I can see your questions, because there are so many messages coming to the chat. I may miss your questions. So let me share my screen now. 1 second. Yeah, I hope you guys can see the screen. So I put the questions here, but the format is, you don't, again, you don't need to write, or you don't need to have any file from me. So the way the questions are asked is actually, somebody is gonna read the questions to you, right? And then you're gonna hear the question and ask the interviewer about some hints. So every time you take a hint, I mean, depending on how many hints you take or how serious the hints are, the power of your solution will go down, right? So our aim is, the ideal thing is, we want to communicate what we are thinking and the way we are planning to solve the problem with the person that is interviewing with us. I mean, we want to solve the problem ourselves, okay? Not with the help of the interviewer. But it's nice, always nice to communicate and then tell what you are doing, what you are thinking, how you are approaching the problem. Okay, so let's start with the first question. Again, I'll try my best to address the problem first as a mathematical problem, and then I'll try to do some coding. So both will happen, right? And let me see please post your questions to Q&A. Again, I may not see your questions if you post them in the chat. So there is nothing to, so I may not share the notebook with you later on. So it's best if you take notes or do it together. You can do the question or answer the question together with me. Okay, so let's look at the first question. So you're drawing once per day. So this can be once per year, once per hour, depending on your time units, a random variable. Okay, so you are drawing a random variable once per day. Again, it can be once per hour, once per minute, depending on your time unit. And that random variable is normally distributed. It's a random variable, say X is normally distributed with 0 mean and standard deviation 1. So just for your information, this was not included in the question. But for your information, so this is the normal distributed random variables, the equation for a normal distributed random variable. Again, mu is the mean and sigma is the standard deviation. So you should keep this in mind during the interview. So somebody coming to a data science interview is expected to know what is the equation for normal distributed random variable. This is the density function, right? So what is the expected number of days that it takes to draw a value that is higher than 2? Okay, so somebody asked this question to us. So we are trying to understand the question now. So every day, a person is drawing a random variable from a sample from a random variable X, and X has a certain distribution. So he will keep drawing day by day until he gets a value higher than 2. Okay, so let's think about this. Day 1. So you picked a value, say x1, and check if it is greater than 2 or not. Okay, so if it is less than 2, then you go to day 2. Again, pick the next sample. If it is less than 2, then go to day 3. Now, and then at some point, say day n, you picked the random variable, say xn, this is the nth number you are picking, and suddenly you realize that, oh, this is greater than or equal to 12. Then you stop. So the question is, on average, so that is why it says expected number of days, on average. So if there were 100 people, and each person is repeating this experiment, and then you just record how many days it takes for each person to get to the number, to draw the number which is greater than 2, how many days it takes for person 1, person 2, person 3, and then average those number of days for each person among 100 people, on average. How long? In this case, how many days? It can be how many hours, depend on, again, how we define a time unit. It takes to draw a number that is greater than 2. So this is the question. So how should we approach this question, right? So there are multiple ways we can answer this question. So you can ask the interviewer, so do you want me to solve this in terms of a closed form solution, like using the distribution functions? Do you want me to solve this using, a simulation? So I personally would like to solve this in terms of a simulation, or I can do both. So again, if you know you can do both, you say I can do both. So let's first try to formulate this problem, okay? And then try to see if we can solve this problem using the mathematical expressions for distributions. If you look at the problem here, the person is drawing number in day 1 and day 2 and day 3 until, so it's almost like failure, 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 and then the first success. So we are asking how many days it takes for you to get to the first success. The moment I explain it this way to you, you remember that, oh, this is actually the geometric distribution, right? So there are a number of trials, and then you stop in the first trial, which gives you the success. So how many trials it takes you to get to the success? So this is actually what is that? This is actually geometric distribution, right? So given a geometric distribution, what is the expected number of what is that? K, right? Until you get to the success. So in the geometric distribution, you have this 1 minus p, and then 1 minus p. So this is the first trial, and then the second trial. Let me put a comma in between, right? And 1 minus p, until you get to a point where you got t. P is the probability of success. Okay, 1 minus p is probability of failure. So you failed and failed and failed, and then finally you got the success. So how many tries it takes for you to get to the success, right? So for that, we are using this expected value. So again, you can check the probability. What is the equation for geometric distribution? But expected value of k, right? So it's going to be 1 over p, right? K is number of tries on average to get to the success. Okay, now let us talk about what P is in this case, because now we reduce the problem into a geometric distribution. Then what is P or 1 minus P in here, right? So what we are trying to see is the number that we draw is whether it is greater than 2 or not. Then P is probability of the number that we are drawing, right? Is, let's use X, capital X is representing the entire set of numbers we are sampling, greater than or equal to 2. Right? So this is P. Okay. Now let's remember what is the distribution of X, right? So capital X, they said it is normally distributed random variable. Okay, so greater than is if we have a number line starting from -infinity to positive infinity, and then have this bell curve, right, above that number line. On the right-hand side, so in the middle, we have the 0 point, which is the mean. On the right-hand side, towards the end of the tail on the right-hand side, we have this number 2, and 2 onwards, right? Any number 2, 2.1, 2.2, any number that we pick 2 or onwards, that is success. So basically, we are looking at the area under the curve, starting from 2 to the right of the probability distribution, if you draw that as a curve. So that is P, right? So basically this is, we can also define this as 1 minus probability of x less than 2, right? Because probability x less than 2 is the opposite, negative, starting from negative infinity up to 0.2, the area under the curve, right? So that is P. Then if, I would ask if that will be sufficient, because if I know P, then take the inverse of P, it's gonna give me the, on average, number of days. Okay, so this is just an opening, so we understood the problem, and actually, if we knew if we can find this P value here, I can easily solve the problem, right? So let's do some coding together and then try to visualize what we taught, and then try to solve this problem. Again, first using SciPy, and then also using some simulation. All right. So I'm gonna look at my notes as I'm typing the code, so that I'm not gonna be wasting your time. Okay. Okay. So first of all, I like using only one library to learn about distributions, because if there are you can use different libraries for probability distributions. I would like to stick to one and then first learn it. So I like using SciPy, and I suggest using SciPy. So let's use SciPy. So from SciPy.stats, okay, I'm gonna import norm. This is the norm distribution, normal distribution. Okay. So next thing is, I wonder what is this value here? What is this guy? Okay, I wonder what is that value. So from normal distribution, this norm comes with its own methods. One of the methods is cumulative distribution function, right? Cumulative distribution function gives us the area under that curve up to the point 2. I'm also going to draw that curve, so just be patient, okay? So norm cumulative distribution function value, all right? So this is a standard normal distribution with 0 mean and standard deviation 1. So let me just insert it is 0. This is the mean value, and this is the scale is the standard deviation, and I'm gonna put the point up to which I will calculate the area under this curve. Okay, so let's see what it is. So it should be a high number, because again, remember the center is 0. From 0 towards the left, it's 0.5, because that's half of the distribution, right? 0.5. And then 2 is towards the end of the tail. So I expect some number pretty close to 1, actually. So let's say this is, let's say, the probability of failure. So any number that I pick from less than 2 is failure, right? So if you pick 1, then you keep drawing this number. If you pick 1.5, keep drawing the number. So what is the probability that you're gonna pick a number which is less than 2, it is 0.97. 0.97, I'm gonna call it probability of failure. Okay, so if that is the case, now let me also just draw this normal distribution for you. Again, this is not part of the solution, but let's just visualize it. So for that, I'm gonna use Matplotlib. So import the PyPlots as PLT. Let me also import NumPy. Okay, so let's import this, and then I'm just going to draw standard normal distribution. So I know that it's between negative infinity and positive infinity, but I'm just going to look at -3 and 3. So that will cover most of the majority of the area under the curve. So let me just define a number line. Okay, this number line is between -3 and 3. Let me form 100 data points. Between -3 and 3, there are 100 data points. And also for your reference, again, I like doing this because I know that from time to time you may also need to write the code for this. So let us also use this function and then write the code for it for a standard normal distribution with mean 0 and standard deviation 1. Let's do it. So first of all, let me write the constant term. Let's call it C. The constant term in front of the exponential function, okay? 1 over sigma times 2 pi, okay? So it's gonna be 1 over. So basically, sigma is 1, right? But let me just write it here for the sake of completeness. And then I'm going to put numpy, okay, square root of. So, or if you like, I mean, you can use star to the power of 1/2. So it's up to you. Square root of this. I'm sorry. Okay. Square root of 2 pi. 2 times numpy pi. Okay, so this is going to be the constant. I hope I didn't miss anything. I think I don't need this guy. Yeah. Okay. Next, what I'm going to do is I'm going to write this exponential term. Okay. So again, mu is 0, sigma is 1. So basically, I don't need to worry about mu or sigma. I will only worry about x. X is this number here. So let me just say this. My PDF distribution, okay, is, so this constant times, now I'm going to take the exponential term, NP exponential. So it's going to be negative. There is a negative sign here, negative x. And then I'm going to take the square root of that. Okay, so negative x squared. So basically negative x squared, and then divide this by 2. Let me just write this explicit. Okay, so this is my PDF distribution. Okay, very good. Move this guy aside. Let me know if it is going too slow or too fast. Okay. Let me see if there are any questions here. So the question is, I'm drawing a number, a random number each day from a random variable normally distributed with 0 mean and standard deviation 1. What is the expected number of days that we are going to draw a number that is higher than 2? How long it's going to take for us on average to draw a number that is greater than 2? Okay, so this is the PDF distribution. Now I'm going to plot this distribution. Okay. So this is my normal distribution. Let me also mark this 2.2 and then fill that out. So just for fun, okay? Okay, so what I'm gonna do is so once I plot this, what I'm gonna do is I'm going to define a list of Boolean values, which are going to correspond to the data points between 2 and onwards. If it is greater than 2, it's gonna be true, right? And then if it is less than 2, it's gonna be false. So what I'm gonna do is, so let me say condition. Okay, condition is the value between 2, okay, or greater than 2 for all the numbers in X. Right. So I'm just using list comprehension. Okay, then I'm gonna fill these points from 2 onwards 3. So PLT fill between, okay, X, my PDF distribution, okay, and then where equals condition. Okay, I think this is going to take care of, yeah. So this is the area that I'm interested in, okay? This is the area which is gonna give me the success, okay? So again, we just did this for fun, all right? Let's continue with our solution. So far, what we found is the probability of failure, which is 0.97. I said at the beginning that this is a geometric distribution. Now let's solve this problem using SciPy as a geometric distribution. So from SciPy stats, I'm going to import geometric distribution. Okay, so as you will see in a moment, it's going to be very easy to solve this problem, right? So PS, this is the probability of success, 1 minus PF. I explicitly define PS and PS so that you know which one I'm using, okay? And now here is the solution. Expected number of days it's going to take. So expected number of let me use n. It's going to take for me to get a number greater than 2, if I draw a number every day, is actually geometric. I'm just going to take the mean, okay? And it's going to be, the parameter is going to be the probability of success. So let me just print this. And PF is not defined. Where is it? PF. We defined it. What happened to PF? Okay. So on average, almost, it's going to take 44 days for us to pick a number. If we pick a number every day, each day, a number which is greater than 2. Okay, we found this answer. Now, I'm just asking to myself, can I solve this problem without using the SciPy library, without using the geometric distribution? So can I just dive into this question and then simulate it and then get the solution, right? That is the next thing I'm asking myself. I'm thinking, how can I solve this problem? First of all, I need to simulate this drawing action, right? How I can draw a number from normally distributed randomness. Let's say I'm gonna create a pool of random numbers which are coming from a normal distribution, okay, with zero mean and standard deviation. That's what I'm gonna do first. I'm going to create a pool of numbers so that I'm going to draw a number from that pool and check if it is greater than 2 or not. And I will count how many days it takes or how many times it takes for me to pick a number from that pool which is greater than 2. And I'm not going to repeat this only once. I'm going to repeat this many times. And then I'm going to take the average of times it takes for me to get a number from that pool which is greater than 2. I hope it is clear, right? So we're going to go step by step. So first, let's create this random number pool of random numbers. So for that, of course, I'm going to use a variable. Let's say I'm going to create a pool of, say, I don't know. So you can be generous and then say 100,000 numbers. So it doesn't have to be that big, okay? It doesn't have to be that. Next. Well, if you like, you can use the equation here and then try your best to create random variables. But let's not go that far, okay? I'm going to use SciPy again, but this time I will use SciPy for, remember, I already imported norm here. Where is it? Here. So I'm going to use norm, but this time sample from a normal distribution, random variables, okay? So I'm sampling from a normal distribution, and this normal distribution, again, has a mean of 0 and standard deviation of 1. And how many samples am I going to get? K number of samples. All right, I'm going to get K number of samples. Perfect. So let me assign this to a variable. Let's call this V. So, and then you can even check the length of V. 100,000 samples I have. You can even check how V looks like. Right? So these are random numbers. Again, I'm not saying between 0 and 1, right? So they're random numbers between negative infinity and infinity, but most of them are centered around 0. Okay. All right. So I have the pool of the random numbers. So next thing is I'm going to pick so I'm just curious. Out of this pool of numbers, what is the probability that I can pick a number which is greater than 2? Okay, when I pick a number, what is the probability that the number that I pick is less than 2? Basically, what I did in here is, here, 100,000, I created 100,000 numbers from this number line. Okay, there are 100,000 numbers here. Some of these numbers are greater than 2, and majority of them are less than 2. So if I count the samples from this 100,000, if I count the samples which are greater than 2, and take the ratio of that to the total number of samples, it is going to give me the probability that I'm going to pick a number from this pool which is greater than 2. Right? So let's do it then. So what I'm going to do is, so I'm going to call this probability of experiment. And this is the probability of failure for the experiment, okay? Probability of failure for the experiment. So what I'm gonna do is any number less than 2. The moment I do this, n less than 2, it's gonna give me. So let me just show you how it's gonna look like. You see, it's giving me true. It's a Boolean variable, right? So I'm checking the first 10 numbers. If they're less than 2, it's gonna be true. If they're greater than 2, it's gonna be false. Okay, so I'm going to sum these guys up. Sum. So this is gonna give me the total number of samples which are less than 2. I'm gonna divide this by the length of my random number pool, right? So this is the experimental probability of failure. Experimental probability of failure. Okay, very good. I got this. Oh, by the way, let me check what I did. 0.97. So let's see what we got before. Where is it? Did I not? PF, where is PF? I cannot see PF. Oh, it's here. I'm sorry. So let's check what we found. I know what we found earlier, but let's check. 0.977. This is coming from the SciPy, and this is coming from our experiment. Okay. Yeah, so 43.9 draws. Okay, let's continue. I forgot to check Q&A. If you have any questions, please post. Okay, so this is our probability of failure. And then, of course, probability of success. Let's also define that. Probability of success in the experiment is 1 minus probability of failure. Okay, we got this. All right, next, what are we going to do? Now, what I'm going to do is, I'm going to assume that there are 1,000 guys. Okay, there are 1,000 guys lined up. Okay, and these guys, each one of them will repeat the same experiment. They are going to draw numbers from that pool, okay, until they see that the number is greater than 2. And then I'm going to count for each person, how many times it takes for that person to get to a number which is greater than 2. So that means I'm going to have 1,000 counts, and then I'm going to take the mean of these counts. That is going to give me the average or expected number of days it takes to draw a number which is greater than 2 from this standard normal distribution. Okay, all right, so let's do it then. So I'm going to create an empty list. This list is going to hold these total number of days for each person. Okay, and I'm going to go for each person. Okay, so I'm going to iterate this, execute this iterative process for each person. I need two, values. One for counting how many times it takes. The other one is the number that I draw, okay? So J will be used for counting how many times it takes for a single person. Now, what I'm writing inside the for loop is for a single person. How many times it takes for this person to get a number which is greater than 2, okay? We start from 0. And Z is at the number that I'm assuming this person is picking. Okay, now in the initial value is 0. Okay, now as long as Z is less than 2, as long as Z is less than 2, okay, the guy will keep drawing numbers from this pool of numbers. So this guy is going to pick a random number from this pool. Remember, the pool is V. Let's remember, D is holding 100,000 numbers. I'm gonna pick one random sample from this. For that, I will use the random package import. You can write the code for how to pick randomly. That's okay, but let's not get into that. Okay, so what I'm gonna do is random choice. So random choice allows you to randomly pick a number from a list. So I'm going to pick a number from my pool of random numbers, 100,000 numbers, okay? And then I will keep counting the number of times I draw from this pool of numbers. As long as the number that I'm drawing is less than 2, I'll keep counting, okay? The first time, it's not less than 2. Second time, not less than 2. Third time, so J is counting number of times I draw. Z is the number I'm drawing. Okay, very good. All right, and then once I'm outside the while loop, I'm gonna append my list. Okay, I'm gonna append my list with J. So you see, my list is holding number of times it takes for each person to draw a number greater than 2 at the end. Okay, wow. Let's run this experiment. Okay, they ran the experiment. Okay, now I want to get the mean of these numbers. So again, my list, it just, look at the first guy. It took 128 times for this person to get a number greater than 2. Second guy, 20. Third guy, 34. So these are the counts of number of times each person tried, okay? So I'm gonna take the average of this, okay? For that, again, taking the average of a list, there are different ways. I'm just gonna turn my list into a NumPy array and then take them. So again, for the sake of completeness, I'm reminding you that I'm using NumPy, okay? Otherwise, I know that I already imported NumPy. And then I'm gonna turn this list into a NumPy array, okay? And then take the mean. And then I'm nervously waiting for the answer, right? So let's see what the answer is. 46.22, what was the answer we found? 43.9, not so bad, not so bad, right? So again, the question was very simple. What we did was we first formulated the question, right, for the reviewer or for the interviewer. We formulate the question, made sure that we made sure it for ourselves that we understood the question correctly. So the first thing is we propose to solve the question in mathematical format. Second, we propose to solve the question using code, using SciPy. Third, we propose to solve the question using a simulation. So we got the same answer for all 3 cases. Okay. Let me see if you have any questions. Okay, thank you, Edward. Thank you, guys. Okay, where did the PF came from? So I just verified here. This is just sanity check. I just verified that this is probability of failure. Okay, probability of failure is any number, the probability of picking any number less than 2. I found PF using the norm here. Where is it? I keep losing PF somewhere. Oh, here. I use the normal distributions cumulative distributive function value. Okay, so I use cumulative distribution function CDF method of norm class from SciPy libraries, SciPy's stats library. So this is giving me the probability of picking a number less than 2. Okay, the area under the curve up to 2. So this is PF. I also checked my PF value by checking from my samples how many of them are actually less than 2. The ratio of numbers less than 2 in my sample pool is also 0.97. So this was just a sanity check. Okay, if you guys are okay, I want to move to the second question, and this took 30 minutes. I was expecting, again, this is the first time I was expecting like 15 minutes or so. Okay, let's look at the second question. What is the purpose of changing my list into a NumPy array? I just wanted to take the mean. That's the whole thing. Okay, so taking the mean of a list. So there are different ways of doing that, but I find this the simplest one. Okay, I turned my list. I know that my list is composed of numbers. I turned my list into an array and then used mean function of array. Well, if you do this, it's not going to work. List doesn't have a mean function. List object has no attribute mean. All right, so let's look at the second question. If I need to go in 30 minutes, if I cannot finish the questions in 30 minutes, we're going to have another session. Okay, so we continue. No worries. Okay, so what is this question telling us? Let's say there are 6 people trying to divide up into 2 equally separate teams. because they want to pick random teams on each round. Each person shows their hand in either a face up or face down position. Okay, so what happens here is there are 6 people, and they just show their hands up or down. Okay, and then depending on how they show their hands up or down, they are going to be randomly split into 2 teams. 3 ups will be in one team, 3 downs will be in another team. So if there are 3 of each position, that means if we have 2 people showing up, 4 people showing down, we keep repeating the experiment. The moment I said that, right? So you see, at each round, there is a failure. And the moment we have the success, we're going to stop. So actually, the first and second question are almost asking the same thing, right? So, I mean, the context is totally different, but what we are looking at is at each round, there is a failure. And then we repeat the experiment until we get to the success. So basically, what is the expected number of rounds that everyone will have to pick a hand side before this? So they're asking how many times on average it will take for us, okay, for us to have an equal split of ups and downs, so that we are going to have what is that? We are going to form a team. So that's the question. Okay, so will you share the notebook at the end of this session? I will try my best. I'll talk to my friends if they can send this to you guys if you register through Meetup. Okay, so let's think about this. Let's think about this. So there are 6 people. And so I'm just gonna use A and B. So let's say if I have, A is up, B is down. Okay. So if I have A, and B, so that is a success, right? And then we'll split into 2 teams, all right? So any case which is not 3 A's and 3 B's, it's not a success. And by the way, the order of A and B will be different, right? So in one round, the first person will be A. In the second round, he might be B. So at each round, the persons being A or B is equally probable. That means it's like flipping a coin, right? So P and 1 minus P are equal to 0.5. Okay. All right. Okay. So let's first solve this problem without any simulation. Okay. And then think about how we can simulate this problem. So the solution should be very simple, actually, right? Let's think a little bit. So they are asking expected number of rounds. Then I should find the probability of success, right? That's what I should find. Well, I should find probability of success and use this probability of success from SciPy John, right? We just learned about it from SciPy stats. Import John, and then John.mean, right? Sorry. PS. That's it. That's how I'm going to solve this problem. Or 1 over PS, because I know that it is 1 over the probability of success, right? So expected number of rounds is 1 over PS. Then what is PS? Let's focus on that, because that is the key. First of all, the most important thing here is recognizing that this is a geometric distribution. This is a simulation of geometric distribution. We recognize that because we are familiar with it from the previous question. Second, if I know the probability of success, I can easily find expected number of rounds. Now let me find probability of success. There are so many books with different good size, and so I don't know really a book which is giving all these aspects, like how we can solve the problem mathematically and then simulation. If you know any, let me know. Okay. All right. So let's continue. Now let's find probability of success. First of all, to have success, I need to have 3A. So if I have 3A, 3B is guaranteed, right? If I have 3A, so out of what is that? So if I say that out of six positions, 3 are A, then you know that the other 3 are B, right? So if any of the other 3 were A, then I will say 4 are A, right? So if I have 6 positions, like I'm just using this, this 1, okay, 2, 3, 4, 5, 6. Now what I'm gonna do is, out of these 6, how can I locate A in many different ways? Okay, in how many different ways I can distribute A over these 6 positions? So that's the first thing. So that will give me the number of cases where I have 3 A's and of course 3 B's, right? So out of the 6 positions, how many of them I can locate? So this is basically a combination problem, right? So if I give you, 6 books and 3 of them are history books, in how many different ways I can put these books on the shelf? Right, it's in how many different ways I can have these history books located in out of these 6 books, right? Combination problem. So number of success cases is then combination of 6 or 3, right? I think that gives us number of success cases. So the next thing is then how many total cases we have. So we have 6 positions. Each position can be either A or B. So the first position can take either A or B. Second position, the third position, basically it is 2 to the power of 6. So I have 2 to the power of 6 different combinations of A and B's. And out of these combinations, and then let me write this explicitly. What does that mean? So is 6 factorial, right, divided by 3 factorial times 6 minus 3 factorial. Okay, so the explicit expansion of C6 with 3, combination of 6 with 3 is this. So if I find number of success cases, this is total number of total cases. Then if I divide, then PS will be equal to, let's say this S, and let's say this T. PS will be S over T. Once I find PS, I can find ER. That's it. So we solved the problem, right? So let's use what is that combination. For that, I'm going to import math. Then math dot combination. So 6 with 3. So this is the total number of success cases. Let's say, let me just run this. Okay, I have 20 of them. So let's make this is equals to this. Okay, and then let me just find the PS2. This is the second problem. PS2 is actually S over 2 to the power of 6. This is the total number of cases. I got PS2. Now 1 over PS2. So this should be the answer. On average, it should take 3 rounds to get the team split randomly. At least 3 rounds. At least 3 rounds. Okay. Actually, at least 4 rounds, right? Because it's 3.2. It should be greater than 3. Okay. So I can also use from scipy.stats. Stats import distribution. And let me find geom.mean and PS2. Okay, I got the same answer. Perfect. Now, can I simulate it? So I like simulations. Okay, simulations will give you a lot of insights. Okay. Oh, by the way, there are questions. Why it's geometry if even in first problem geometry, because remember the geometric distribution, we are looking at the number of trials it takes to get the first success or failure. So depending on how you define success and failure. So, okay, so that's geometric distribution. Okay, now let's do this. Let's simulate it. So for the simulation, I'm going to be using again random library. So what I'm gonna do is I'm gonna repeat this experiment 10,000 times. Okay. At each experiment, I'm gonna count number of times it takes to form a team. Okay. Similarly, what I did earlier. So in this case, 10,000 is like 10,000 people. Here, I'm repeating this experiment 10,000 times. Each time, I'm gonna count how many times it takes to form a team. So how many rounds it takes, and then I'm gonna average them. So here are the outcomes. Let's call it A and B. So, okay, this is the outcomes. And I will keep the number of rounds in this list. Okay. And I will also, what is that? I will also count, what is that? What is that? How many times it takes, okay? With a variable J. Okay, so for I in range of K, so this is how many times I'm gonna be running this. So for each experiment, this is the group that I'm gonna be, so this is the A and Bs. Okay, I'm gonna be keeping for each round, I'm keeping A and Bs. Okay, you can write this code in many different ways. I'm writing in the most explicit way that I could think of. Okay, so there are 6 people. Each person will pick either A or B, and I'm gonna put that A into the group. Okay, so for each person, I will make a random choice. Okay, from outcomes, and let me also make this. Let's take the next line and then go. Okay, so for each person will pick randomly from A or B. Okay, and then I will append that here. I will append that to my group. So my group is holding A's or B's for each round. Okay, all right, and then after I'm done for this round for 6 people, now I know each person A or B. I'm just going to check. I'm going to check if my group, okay, if my group, I'm going to count how many A's are there. If number of A's is 3, that is the case. Okay, if that is the case, I will just add J with 1. And then let me also assign J to 0. Actually, I don't need my list in this case. Probably I put it my list here from previous code. Okay, now let me run this. Let me run this code. So you got it, right? So I'm repeating the experiment for 10,000 times. Each time I'm asking the people to pick A or B. Once the group is completed, I'm just counting how many times it takes for us to what is that? For us to find the probability, the correct probability. And by the way, it's PS here. Yes. PS. Yeah. Okay. So this is the PS2. Remember, this is the probability of success for this experiment. I'm just going to compare this value with this value here. So let me run this first. Okay, and then this is actually that it's going to give me P2S experiment is J over K. So let me print this value here. 0.307, 0.3125. I mean, almost the same. So once you find this probability, the rest is very similar to what we did in here. So, well, if you like, we can do the same thing. Let's do it for exercise. Again, this is just probability. Now I'm going to repeat this experiment with this probability and then try to see how many, on average, how many times it takes. So let's do it. Again. Okay, here is the different thing in here. Just, I hope you guys are not lost or we didn't lose each other. Yeah, combination, the point why we are using combination is I'm trying to find out of 6 positions, how many combinations will give me 3 A's. That means 3 B's. Okay, here is what I'm gonna do, okay? So far, we found the probability it takes to form a team at one, to form a team. So how many out of 10,000 trials, in how many trials we were able to form a team, okay? In how many trials we were able to form a team. That's what we did. And this is the probability of success, okay? Okay, now what I'm gonna do is, with this probability of success, can I simulate how I can find the average number it takes to get the first success? Okay, can I simulate the process, which is gonna give me the number of trials it takes for me to get to the first success? Can I simulate that? How can I simulate that? Okay, let me write what I'm saying. I know that you are tired and you don't have much time left. So how many times it takes, how many trials it takes to get to the first success, okay? On average. Can we simulate this? So this simulation is different than the first one, okay? A bit different than the first one. You'll see the difference. The slight difference, but it is important. This one is important because you can use this for other simulations later. So now I'm gonna use a third distribution. So far we saw normal distribution, geometric distribution. Now I'm introducing a very important distribution, which is uniform distribution. So uniform distribution is very simple in this case. So we are creating, we are sampling a number between 0 and 1. And the probability that we're gonna pick a number from between 0 and 1 is all the same. So the probability that I'm gonna pick 0.2 or 0.4 or 0.5 or 0.6, all the same, okay? That is uniform distribution, okay? Now what I'm gonna do is, I'm going to pick a random number from this uniform distribution. So remember, between 0 and 1, it's equal likely for me to pick any number between 0 and 1. I'm gonna pick a number, okay? I'm gonna compare this number with my probability of failure. If this number is less than probability of failure, then I will assume that I failed in this experiment. If this number is greater than probability of failure, that means the number I picked is in this region. Okay, so just imagine, now I'm talking about uniform distribution, but just imagine that the number that I'm picking is in the success region, if it is greater than the probability of failure. If it is less than probability of failure, I will assume that I failed in this experiment. Okay, so let's do it. I'm going to repeat this experiment for 1,000 times. So now I need my list, because this list is going to hold the number of trials. So for I in range T, I'm repeating this for T times. Again, similar to what I did earlier. So J is 0. Remember the first time we used this experiment, Z is 0. Okay. Remember last time I said while Z is less than 2. Remember that? We used that while Z is less than 2. 2 is the threshold value. Here, our threshold value is actually probability of failure. Okay. While Z is less than probability of failure. So we found the probability of success. So I'm going to use 1 minus this value. 1 minus P2S underscore exponential. So again, imagine that I have a number line from 0 to 1. Out of this number line from 0, between 0 and 1, from 0 to probability of failure, any number between 0 and probability of failure is representing the region where I will fail. Any number between probability of failure and 1 represents the region where I will succeed. Okay, so I'm going to pick a random number between 0 and 1 and see to which region this falls. Is it falling into between 1 and probability of failure, or between probability of failure and 1? I'm sorry, between 0 and probability of failure. Let me write it. Between 0 and probability of failure, P2 failure experiments, it is failure. Between probability of failure experiment and 1, it is success. Okay, that is how I will use this uniform distribution. Okay, so I will create a uniform distribution. Z is a random variable, a sample from uniform distribution random variable. So this uniform RVS, let me run this. Sorry. I know that it is coming late at some part of the world, and then you guys are tired. I will stop in a moment. Uniform. Yes. Okay, so it's creating, every time I run this, it's creating a random, it's giving me a sample from a uniform distributed random variable between 0 and 1. So I got Z, again, every time Z is a single number. And then what I'm going to do is, as long as Z is less than this probability of failure, remember 1 minus probability of 2 success, this guy, let me write this here explicitly so that you will not, let me write it here. This is the second experiment's probability of failure, okay? Now let me write this here, P2F. Okay, so as long as it is less than the failure, so I'm checking this part, it is considered as a failure, so I will keep counting. Okay, I will keep counting J. I will just keep incrementing J. Again, J is holding number of times it takes for me to find a uniform distributed random variable which is greater than the probability of failure. Okay, and then I will repeat this experiment 1,000 times. Okay, so let me append this J as I did earlier. Okay, perfect. Now I got my list. So let me run this, and it gave me an error because another one goes. Okay, I got it. All right, so I'll do the same thing. Import again for the sake of completeness, as we're writing here NP. So I will turn my list into an array and take the mean, and hoping that I got the similar result. What was the result? 3.2. Let's see. 3.2. Okay, so this concludes the simulation for the second problem. I hope it was not too slow. I tried my best to explain what I'm doing within my ability. I have 2 more questions, but I think I should stop now. We're going to have a second session of this, and then I'm going to add more problems. Okay, so please let me know if you have any questions during the sessions. And let me just check before we go. White's geometric series even in the first problem, because in the first problem too, right? So what we were doing was, so there is, every time we pick a number, if it is less than 2, it is a failure. So we pick a number until we get to the point where we get a number greater than 2. So that's a geometric distribution. The point, yeah, I explained that. Okay, thank you. So you will receive an email about the second session. The only prize that we ask for this session is please write a review for us. Okay, so let us know how we are doing. It's very important for us. It's very important for me. The only thing I'm asking from you, please write a review for us. Okay, thank you so much. I'll see you in the second session later. Okay, take care, guys. Bye.